Hello everyone, welcome to another Math Club talk. Today we have with us Nikhil Nagaria from B3. His interests are in algebra and combinatorics. He is going to give a lecture series on Introduction to Combinatorial Game Theory. Today is the first talk on Nim and Bouton's theorem. Over to you.
Thank you for being here. So, as I said, this is a talk series of 8 talks on the subject of combinatorial game theory, and through this talk series, we'll slowly. There will be 3 talks. The first talk will be basically developing a lot of motivation to why this, how things work in this subject, and we'll see one of the earliest theorems in this subject called Bouton's theorem, and slowly in the second talk we'll then develop some more definitions, we'll develop some more notions, and we'll conclude by proving one of the biggest theorems in combinatorial game theory, at least in this combinatorial theory. It's called the Sprague-Grundy Theorem, and at the end we'll also look at some more results about simplifying games, simplifying forms of it. Okay, anyway, so to start, combinatorial game theory, where as the name suggests, we're going to talk about games and some special kinds of games. And okay, so those are called combinatorial games. And what happens in a combinatorial game is you have essentially a 2-player game where the two players make alternating moves, and I need to assume 2 things, which is the first thing is that there is perfect information. So this is a terminology more common in the other games, right? But anyway, what perfect information means is that the information available to both the players about the game is the same. No one has more information than the other, no one has different information than the other. For example, in most card games, you only know your own cards, you don't know the other person's cards, so that is not a combinatorial game because some information is only available to you. And the other condition is that there is no random elements or no randomness. And more precisely, well, you could just take it to be like there's no probability, there's no dice, there's no coins. Everything is deterministic. The effect of a move is already known before the move is done. So essentially, and I'll just write this down just for this time. There are common examples. Examples include tic-tac-toe, because you can just convince yourself that, well, there's nothing hidden and there's no dice inside. And maybe look at chess. And in fact, yeah, because again, in chess, same words. And there's also this game called Connect, so if you've seen. And boxes, and so on. There are several examples that we know of, but unfortunately, these are very hard to study. The games that we rather study are simpler than this, and in fact, so none of these are things that we are going to see even something close to in this lecture series. And what we are going to study instead is these combinatorial games with the imposition that the winning rule is whoever makes the last move wins. So whoever is unable to move loses, essentially. And this is such a name, it's convention, it's called normal play. Whoever can't move loses, and that is what we are going to look at for this entirety of this talk series. But there's another convention, and that makes the theory a little difficult. also quite interesting to look at. It's called Michel play, and it's the exact opposite of this. If you can't move, you can instead. And so these are the winning conditions that we impose, and instead you can notice that in games like in these 4 games that I've written down there, this is not how the winning condition works. A winning condition in testo, for example, is when you hit a diagonal or a row or a column of your code or Excel, which is definitely not this. And similarly in this, and you could interpret them in some way, but still these games are fairly complicated. Okay. And then the next thing is, so what do we do in this subject? And I mean, it's not too hard to guess. What we do essentially is just to see how to win at these games. We see how to solve these games. And solving means maybe finding who has the winning strategy, which player has the winning strategy, how can they win, and so on. And in fact, there are several levels of winning which are not too relevant to what we are going to do, but they go into some other branch of the subject. But I'll just give a few names. So we have games that are strongly solved. Strongly solved games are those where we know everything about the game. From any position, I could tell, okay, this player is going to win, and this is the winning strategy that this player has, and if they just follow it, they'll win, no matter what the other player plays. And then there are weakly solved games where, suppose you only have the winning strategies from the starting position. And an example of this is Fox and Geese. You can find it on the suppose more information. But yeah, so what happens there is we know how to win from the starting position. But from arbitrary position, if the winning player deviates from his optimal play, then okay, we are lost. And then there are also games that are even weakly more weakly solved or ultra weakly solved, in which we know which player has the winning strategy, but we don't know what the winning strategy is. Which might seem surprising, but it's common. If you do more maths, you'll see that there are some times where you prove the existence of something without giving an explicit construction. Okay, so with all of that, let me just start. And so today, for this first talk, what we are going to do, the main goal is to solve game of Nim and Bouton's theorems are exactly the theorems that tell us how to win a game. And before that, so the solution to Nim is somewhat, it's not the most trivial thing, but so that's why I like to do some simpler games, and then let's go and then move on to example. So to start, I'll introduce this game called Kayles. And the game is as follows. So you have a bunch of bowling pins or bottles or whatever lying in a row, and then a move is to knock down one or two adjacent things. So for example, at this stage, a move might be to knock down this pin, and just clarify these two are not adjacent anymore. And then the next player can maybe do knock down these two pins, and then the next player moves down these two, and this, and then whoever moves the last one is the one who wins under normal play because their opponent on their next turn cannot move. And in Michel play, they instead do so. Okay. So these are the rules of Kayles, and turns out there is a very simple solution to Kayles under normal play. And again, by a solution, I just remind you or mean that I am going to tell you who is the winning strategy. So, what is the winning strategy? The winning strategy is very simple. So, I have a row of bowling pins. Say I have 9 pins. Now, the winning strategy is so I claim that the first player can always win this. unless there are no pins. That's a trivial regenerate. So suppose there are 9 pins. The strategy for the first player is to remove down the middle pin on their first move, and after that, the game, as you can see, is broken down into 2 disjoint components. And what I mean by disjoint here is, more precisely, a move made by any player after this point can only affect one of these components. So both of these components are truly disjoint, and this is this breaking down of a game into disjoint components is very, very central to this theory, as we'll see soon. So, and now to continue, the strategy for the first player now is to make sure that the pieces look identical at each step. Currently they look identical, and suppose the second player makes a move, let's say they move this pin. Then you just copy it here and then use this pin. Now if the next player say moves this pin, these two pins, you move these two, and then the second player is forced to move one of these. The first player is under normal play. So under normal play, this strategy works very neatly, and in fact, if you have an even number of pins, all you have to do is to knock down the middle 2 pins, leaving the exact same consequence. So this is a very simple symmetry strategy for this game Kayles under normal play. Under measure play though, this game is quite hard to play, and in fact, historically, I think there was a gap of around 40 to 50 years between the solutions of normal Kayles and measure Kayles. Okay, and this strategy that we have seen is called, well, of course, this symmetry argument is very common in math, and in combinatorial game theory, sometimes it's called the mirror image strategy, or the equivalent argument, and that is a very funny name. So one of the founders of the subject, Conway, he is very famous for giving all of these kinds of names. For example, there's a monster group in group theory, and there's a monstrous moonshine, whatever that, and here we call this a equivalent strategy, because equivalent and equivalent are 2 identical characters in some American mythology. Okay, so this is all about Kayles, and then I'll do one more game. So let's do that. And this is called Chomp. And how Chomp works is, so how Chomp works is, you have a grid, or you could imagine it as a chocolate bar in which case the name being movement, as you see. So suppose you have a chocolate bar. Suppose you have a bar, a grid, and a move here is to pick any of these. Okay, so I'll also mark down this square. I'll explain why. So now a move is to pick any of these squares and remove all these squares to the up and to the right. So for example, if one picks this square, then you remove all these squares up and to the right of it. So it leads to this, like this. And so this is like exactly like, imagine this is a chocolate bar, you want to eat this, but you can't just take this out, so you have to do all this. So whatever. So this is the move, and of course you can't ever pick this square, because otherwise the game is too trivial. The first player can just always pick this, and so in that case it's not so interesting. So that's why the first player can never pick this. And for example, let me just continue on with this board, for example. So let's say the next player picks this square, and then you just remove these two. There's nothing to the up. And then say if this is square, then all of this is gone. And the game will continue like this. Again, at some point we'll hit this square, and at that point the person who has to move cannot become moved, and so they lose under normal play. And from now on, I'll just always talk about normal play. We'll just ignore this, because this is quite hard to do. So for the purpose of this and the future 2 talks, we're only going to talk about normal play. So here, and this is one example of a game which I mentioned earlier, that there are games which we know who requires a winning strategy, but we don't know what the winning strategy is. This is one example. And so, let me write down this theorem. It's a first pair ring. Well, of course, it's unless there is only the Poisson square, or not quite only the marked down square, in which case the first pair immediately will. So unless it's a 1 by 1 grid, count the pair. So let's just write that. And the proof of this is as follows. So let me reconstruct the grid. Label these squares. So suppose this is a y grid. I'll call this square 1 and call this n comma 1. This is 1 n. So some standard level. So with that I can start the proof. So if 1 comma 1 is a winning move, then what that means is, if by picking this 1 comma 1 square on the first move, the first pair can ensure that no matter what the second pair continues with, the first pair can find a winning continuation, then we are done, because that's essentially what we are claiming. So, suppose then, so if 1 comma 1 is not a winning move, what that means is that the second pair instead has a winning counter to it. For example, let's say at some a comma b here. So suppose not, then suppose there's a winning counter. Let's call it a comma b, and necessarily it's not 1 comma 1. Then, so now what happens is that, so the first pair picks this square, this square, and then the position is this. So let's call this E. Then, what has happened is, since this was a winning counter, and now first pair has to move here, so no matter what the first pair takes, the second pair can continue finding winning continuations to this. So, in other words, whoever has to move next on P loses, because the player after that can keep finding a winning continuation by assumption, because this is a winning counter. So, whoever has to move from P loses. And once we have this, then the first pair would simply go to A comma B on their first move, leaving the second pair to face this position and therefore lose. And so this completes the proof. But you can notice that this proof tells us nothing about what is the winning move. Either 1 comma 1 is a winning move, or well, this whatever this A comma B is, that is a winning move. So we don't know what the winning move is, but we have shown that there is a winning move that the first pair has. Okay. So yeah, okay. With all of these simple examples, now let me get down to Nim. So another game, and the game is this was also described in the abstract. I don't think I called it, but so there are a bunch of files or points. That's it. We have 3 files of 4, 5, and 2 points. So a move is to pick any of these files and remove some points from it, and a non-zero number of points. So for example, if I were to move from here, I would remove 2 points from this. Or the next player to play would suppose pick this file and remove just 1 point. And then if it's my turn, I can suppose remove all of these points. So yeah, you are allowed to remove all of the file at once. So there's nothing here. And then so on. And again, you can have the normal segmentation where if a person who has to face the configuration where there are no points loses because they can't pick up. Okay. So this is what Nim is. And some simple solutions that we can right away see. So our goal is to solve Nim, describe where the strategy and what is the strategy. And in 1 or 2 points, it's very simple. So for example, let's say, suppose there is only 1 point of n points. Then it's very clear that the first player can just win, right? Because they can just pick all of the points on the first point. And so, let me just set it this way: if n is not 0, then it's the first player, because n equals 0, but other 3 will 6. I wouldn't call it a 1 point, whatever. So if you have a simple scenario like this, where there's just equal number of points in both of them, then you could follow an argument which was, you can follow this argument again. You could, whatever the, so for example from this I can claim that the second player has a winning strategy, because no matter what the first player does, well, the second player could just make sure that both the components look the same, and it's essentially just this, put in implemented. So write that. If A equals B, then it's the second player, right? And if A is not B, then the first player has a winning strategy by simply making them equal. One of them has to be larger than the other, and they can just make them equal on their first move, and then it's the exact same thing. That's the first player. For example, if there were 5 and 3 points, the first player could win by making it 3 and 3, and then continuing with the symmetry. So these are very easy to analyze, and they are just essentially a simple symmetry argument. But the general case where you have more than 2 points is a little harder to handle, and that is what we'll do. We'll see how Bouton's theorems will state them and see how they help us in solving it. So, let me okay. So, I need to introduce some notation. So, let's say you have two positive integers. Well, non-negative. Let's say you have two non-negative integers. Then I will define an integer called a, and this is read as nim sum. I'll define this new integer called a nim sum b, and how that works is you write both a and b in binary, and you add them without carrying. And so let's try an example, because it definitely sounds complicated. Let's say you have 11 and 13. Now 11 in binary is 1, 0, 1, 1, 13 in binary is 1, 1, 1, 0, 1, right? So what you do now is you add them without carrying. So 1 plus 1 is 10. Normally you would put a 1 here and carry that over, but here I'm saying you don't do it. And then you just continue. So 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is again okay. So just keep it straight. And so this we converting back into decimal, this is 6. So what we have said is 11 times 13 is 6. And you could even write down this more formally by just write down A as a sum of powers of 2, write down B as a sum of powers of 2, and then say that you remove the common powers, add the remaining powers, whatever. But this is a very precise definition enough, and we'll just work with it. And so now I'll like to state some simple properties of this, which we'll use. Properties are, well, some trivial things I would say are commutative and associative. There is not nothing to deep into. At nim 0 doesn't affect. Okay, and the last property is the only one, but it's also very. Two things lim sum to 0 if and only if they are equal. This makes a lot of sense because the only way you could get all zeros here by adding two numbers is if both of them are same at every place. That's exactly what I'm saying here. And for the people who know this is just saying that the positive and non-negative integers under this operation is an abelian group of exponents. Okay, if you don't know what this means, so with this I'll introduce some more. I'll introduce so how does this help in solving Nim? And that is, so what we'll do is suppose you have an position where there are k piles with n1 and dot 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 and k points, then you name some all of them, and that is what you call its new map. And one more definition. Another definition. You call a position a zero position if its nim value is 0. And yeah, this is pretty much it. And I'll call it non-zero. Okay. And why this definition is because if you notice, if I come back here, you notice that here this condition can be replaced as and so you notice for two piles, if the position is 0 position, then it's a second pair win. If it's not a non-zero position, then it's a first pair win. And in fact, you could just look at that in the one pile case as well. Because for a one pile, the nim value is just whatever the number of points is. So if it's non-zero, then it's the first pair win. If it's 0, it's the second pair win. And that is exactly what we will see soon. Is that if any 0 position is a second pair win, and any non-zero position is a first pair win. And to see that, we need the Bouton's theorem. And so let me. start right away with Bouton's theorem. It has two parts. So I'll state them as let me call them theorems. So theorem A. What this is saying is that if you move from a zero position and as a nim move, so if you have a zero position, which means you have a nim position with its new value is zero, then if you make a move, any move from it, will have to be to a non-zero position. And you see the proof of this, it's just simple manipulation. Suppose you have a zero position and not particular 10k, and let's say that the move is without loss of generality, as if the rate is in n1. So without loss of generality, assume that the move is from n1 to some a is then forced to be smaller than n1. Okay. Then what we want to say is that a in some n2 some dot is non-zero. So notice then. So we want to show that this is non-zero, and the simple trick here is to squeeze in this n1 plus n1 here, which we know is zero, so I could do that, and then I can look at, notice this, all of this is zero, so all I have is simply a in some n1, and since a cannot be equal to n1, this cannot be zero. And this completes the proof for the first step. So essentially, what we have showed is that when you move from a non-zero position, from a zero position is a non-zero position, and then I will have here. Tells us that if you have a non-zero position, then all moves don't have to be to zero position, but there is at least one move that is to a zero position. And before I write down the proof of this, I want to motivate the proof because the proof is a little complicated. Just look at it. Let's do a little example. Let me have the numbers. So let's say you have 13 plus 12. I'll just call this plus because I have too much to call it. So let's look at this. So to compute this, you have 0, 1, 12 is 1, 1, 0, 7 is 1, 1, 1, so 0 here. And the name of this, well, it can be easily computed. It's 0, 1. Yeah. So it is 6. Okay. And which is not 0. So now I think that there's a move to a 0 position. So point is I would change one of these numbers to a smaller number such that this nim sum becomes 0. And if I just think of it as a simple puzzle given to me, I notice that okay, so I have a 1 here, I want to have a 0 here. So you notice that this one is here because there's an odd number of ones in this column. The entry in a particular digit only depends on the corresponding digits in the sum. Okay. I have a 1 here, but it's here because there's an odd number of ones. So I just pick one of these ones and I just say make it 0. And then this will come again. And then I have this one here, and then I just change this 0, go on, and now, yeah, and this one. So that is the idea. The idea is you find the largest, find the first occurrence of 1 in this final sum, and in that term there's an odd number of ones. In particular, there's at least one of them. So you go to that, and then you change it to a 0, and then you modify the rest of them in that same number so as to make the final thing 0. In our case, this is this is 11. So in fact, you could check that 11 and 12 and 7 is 0. Or what we could have done instead is we could have like we had originally here. I could have picked any of them. I could have picked it, say, this one, and then change this to a 0 and this to a 0 as well, taking the final sum 0. So in this case, 7 to 1, we should notice that again, giving me and with that idea there, let me write down the proof. So say you have a position whose new value is x and x is not 0. Then so let so again the point is like look at x and look at the first bit. So that j is and I start with counting bits from here. So this is the 0th bit, this is the first bit, this is the second bit, and so on. So let's suppose that j is the largest such that jth bit of x is 1. Then there are an odd number of ni's which have 1 in their jth bit because they sum up to x and x is of 1 in the jth bit. So without the loss of generality. So in particular there is at least 1. It can't be 0. So without the loss of generality, say n1 has a 1 in its jth bit. Then I want to somehow modify n1 and make this nim sum 0. So if I just again go back to this example, and notice very carefully what we are doing. What we are doing is suppose I pick this thing. Now what I do is I change wherever there is a 1 here, I like to change that bit to what the other thing. So if there is since there is a 1 here, I'll change this to a 0. Since there is a 1 here, I'll change this to a 1, and so on. Only the ones where there is a 1 here, I'll flip the corresponding bit here, and then that is enough. And doing this, if you just notice, all I have to do is if I nim sum this with this, what that will do is just all the ones will change the bits and the zeros will leave those intact. So all we are exactly doing is just lim summing this with this. So let A x lim sum n1. Then well, of course, now if I just compute the final lim value, I have this, and I substitute A for x lim sum n1, and again this all of this just becomes x. So I have x. But okay, you might be thinking, oh, this is done, but it's not, because you need to show one more. You need to show that this A is strictly smaller than n1, because what if it turns out to be bigger? Then you can't even make that bigger. That's not legal. So I have to prove that A is smaller than n1. That's what we will all this part of the for. And to see that, I'm going to say, okay. So intuitively, what is happening here is x, the largest bit for which it is the 1 is j. So when I'm lim summing x with n1, the bits after the j bit, the bits on the left of the j bit, are the same in a and n1, because for x it is 0. And for the j's bit exactly, it is 1 in n1 and 0 here, because there was a 1 here. And for the rest, well, so say I have x something and n1 then by assumption in the jth bit I have a 1 here, and beyond this it is all zeros. For n1 I also have a 1 here, and beyond this there can be anything. When I lim sum this, all I get is whatever this was, this will get copied exactly as it is, and here I have a 0 and whatever there is. Now this is strictly smaller than this, because it has the same bits up to this point, and then in this place there is a 0. So it's very clear that this number is smaller than this number. So then A is smaller than n1, and so the move is valid. And so what we have shown here is that yeah, so this is a legal move, taking this non-zero position to a 0 position. And in fact, you could slightly generalize, slightly strengthen this by saying that there is an odd number of moves to a 0 position, because for every such ni, which is the 1 in the j bit, we could find a corresponding value, just like we had here. Okay, so these are the two theorems of Bouton, and with that I think we can write down the solution names. Corollary to these two theorems. So why is that? I am not going to write down the proof here, but I will explain it. What is happening? So suppose let's look at this case first. Suppose n is 0, so the lim value is 0, so 0 position. I want to say that it's a second pair ring, meaning no matter what the first pair moves, the second pair can find a new continuation. Okay. So what happens when the first pair makes a move from a 0 position? By theorem A, it's to a non-zero position. And then the winning continuation I claim for the second pair is to use theorem B and find a move that takes it to a 0 position. So then the first pair is again faced with a 0 position, and again then the first pair will make a move to a non-zero position, the second pair will continue, and it will keep on happening, and at some point we hit 0, at some point we hit the configuration with no points because points are going down at each state. So but a 0, but the configuration where there are no points is a 0 position, and the strategy that I have described, only the first pair will be the one to face a 0 position, because the second pair is ensuring that they face a non-zero position at each state. So therefore the second pair is the winning strategy. That is the winning strategy. So let me let's type it down. So if n equals 0. If n equals 0, and the second pair ends by making it a 0 position at all times. That's the winning strategy. And if n is non-zero, then again this is somewhat reminiscent of the original analysis that we did. If n is non-zero, all we have to do, so it's a first pair win, because the first pair could now use the theorem B, go to a 0 position, and then the second pair is the one facing this losing position. So if n equals 0, first pair wins. Yeah, and that's something. So this solves the game of Nim. And so this is how you use Bouton's theorem to solve Nim. And this is more or less the main content of my talk. I'll do some more stuff which will motivate the things that we will do in the next talk before. And now let me do that. Put that here. Okay, and in fact, let's just do an example as well. So let's do an example and follow this strategy. So let's say we had, let me take some smaller numbers. Let's say you have 7, 9, and 6. Let's compute the names of my users. I hope it's not 0. 1, 1, 9 is 8 plus 1, 6 is 1, 6, 1. So I have 1, 1, which is non-zero, right? So according to our claim, the first player can now first player can force a ring by going to a 0 position. So to go to a 0 position, I have to go here, find this one, make it a 0. So this a 0, and then I will make these two, I will break this as well. So I'll have this. So my winning move is to go to 7, 2, and 6. Okay. And now this is a 0 position. Now no matter what the other player does, let's just take let's say it goes from 7 to 3. And then we will do this again. So let's say 3, 2, 6. And 0, 0, 1. So I just need to change this to. So this is the first player switching to position diagram. First pair, first pair. Okay. And from here, let's say the second pair goes in, let's say from 3 to 1. And the first pair will remove by removing this one. And yeah, so this is an example. And okay, so now let me go to have enough space here. Okay. So, in general, how we'll work with. So this, in fact, let me point this out. This is a these are very nice proofs, and this was a very nice solution. But most of the time, what we do in this subject is work a little differently, and so the general theme of this subject is you study and solve games by assigning them values. And if you have ever played chess, you will notice, well, in chess you have an evaluation bar on your side, which if it's positive, it means white has a winning advantage, and the amount, the magnitude of that denotes the amount of advantage that white has. And if it's negative, then black is an advantage. If it's like 0, then well, it's like a draw. It's kind of neutral. So exactly in that way, we do it here, and I'll give you an example. I'll introduce another game. Say you have a grid. Let's say you have a grid and you have two players A and B. Let's say A has, and both of them have pieces on this grid. So let's say A has that piece there and B has that piece there. Now, okay. So a move for A is to move any of his pieces, any number of squares to the left in the same row, and for B to any number of squares on the right in the same row. So for example, A could move here or here or here, and B could move here. And outside you'll notice that it's very dumb to move more than one square at any point, because well, that's just cutting off your own move. So in fact the only good moves for A is from here, then here, then here. For B to go here, then here, then here. Okay. So in this specific position though, you'll notice that effectively A has 3 moves to play and B has 2 moves to play. And so A will win no matter what. To just do an example, let's just say, so suppose A goes here, B goes here, A goes here, A goes here, A goes here, and now B cannot make a moves of these. And similarly, if I had, and okay, here in this case it's there the 2 players A and B are very different from the first and the second pair that we have been seeing so far. So now I need to make a distinction. A can be the first pair, B can also be the first pair, and that is 2 different analyses. So if A starts, well, yeah, as I said, A goes here, B goes here, B goes here, B goes here, A goes here, and then B loses. But if instead B started, B will go here, A will go here, B will go here, A will go here, and now B cannot be known, so B loses. So what has happened here is that no matter who starts, whether A starts or B starts, A is the one who is going to win, and we all know why that is happening, because A has 3 moves to spare and B has 2 moves. So in fact, again with that chess bar analogy, I'll assign the value +1 to this position, and +1 because 3 moves for A and 2 moves for B, and so it's like +1. And again, the plus, to clarify once more, plus will mean that A has a winning advantage. The number here will tell us how large of an advantage that is. And similarly, if I had said, let's say A here, yeah, then this would now be 2 minus 3. Right? Because now A has only 2 moves and B has 3 moves. So this is assigned -1. And the interesting case is what happens if I have this. So in this case, it is 0. Who wins in this case? And it's very easy to see that since both of them have an equal number of moves, whoever starts first will run out of their moves first. So if A starts first, A will lose, and B starts first, and B will lose. So in fact, it's a second pair win. And yeah, and I mean, clarify by second pair win, I mean whoever starts second wins, no matter whether it's A or whether it's B. And the interesting thing to notice here is that, well, 0 in the second term, I had exactly the somehow in this, the way I described assigning values to you, and the nim value of nim position, both of them in some way turn out to give me like, well, if the value is 0, then it's a second clear win. And this is no coincidence. It happens, and we'll see, as we'll see in the next talk, we'll see why assigning the value 0 to a second clear win position makes sense. And in fact, I've been calling it 0, so we'll see how to add these values and turn it as it will turn out. Second pair wins will be the additive identity of whatever is. So to continue, so let me write down something here. So let's say we have a certain position in this thing, and it has a value g. Then what we have seen so far is that g, if g is bigger than 0, then A wins. If g is negative, then D wins, no matter who starts. G is equal to 0, it's a second pair win. And there is a problem, and we run into some problem here, because these do not exhaust all the possibilities while these do. I could have a first pair win. Why not? And a concrete example of that is, let's say, so now A on their move would just move here, and we can't jump over, so A wins. And similarly, if B starts, B goes here, and B wins. So it's a first level, and we would also definitely like to assign this a value, though we have run out of things to, well, at least, yeah. You see, it can't be positive, it can't be negative, it can't be 0. So we have run out of things, and well, it turns out it has, we'll assign it a value, and it won't be any of these. For people who are familiar, who have ever seen a partial order in math, they'll know that this is very common. You can have partial orders on set where you can't compare necessarily all the things. So some things can remain incomparable, like this. And I'll just give a simple example if you know. So if you, for example, in R, you can compare any two. If given any two real numbers, I can tell which one is bigger and which one is smaller, or if they're equal. But in say R2, suppose I define this order. A comma B is less than C comma D. Okay. A is less than C and B is less than D. Then with this order, you'll notice that 1, 2 and 2, 1, they are not equal, none of them is bigger than the other. They are incomparable. And yeah, and this is exactly a partial order. So we'll see this in the next talk as well. We'll see more precisely what this partial order is and how it works. And for now, so yeah, the first pair wins, you assign a value that is incomparable with 0. And so I'll go back, just a funny thing, was that, as I said earlier, Conway was one of the founding people of this subject, and he is very famous for giving funny names to things. He called this, well, he could call it incomparable, definitely, but he called this confused. Say, well, I'll read this as G is confused with 0. That's just, well, and there are more funny things, some of which we've seen, some of which we won't. For example, there are games that are called star, up, and down, which we'll see in the next class, next talk. And there are things called tiny and tiny, but those we won't see. There is also a branch of the subject called temperature study, where we study temperatures of things. As funny as it sounds, it's very interesting, and but we won't do it in these talks. It's a little will take a lot of time to develop that. And in temperature theory, and there's a theorem which says that you can if you have any gain, if you have any position which is a value, you can suddenly dissociate that value into particles at certain critical temperatures. Well, yeah, for sure. And then you can also have atomic weights and stuff. So let me stop this. We are talking about funny things. And going back to what I where it was. So the general scheme is to assign values to games, and then we'll see that we'll give them a partial order. We'll also give them a addition. So we'll given values g and h. We'll define what it means, what g plus h means, and then we'll see that we can in fact give it a abelian group structure. So if you know what that means, good, and what that really all that means is that I'll define g plus x such that it's associated. This 0 will serve as an additive identity, and for every game I have a additive inverse, I have minus g. And yeah, and the really final thing of this first talk is I'll mention an informal version of the Sprague-Grundy Theorem, which we are going to prove in the next class. And to prove that, I'll define the first. So I'll call a game impartial. I'll call a game impartial if the moves available to both the players are exactly the same. And for example, and these are exactly the games where you only have two conditions. Well, where you don't need to worry about who is starting, because both the players are in some sense indistinguishable. For example, in Nim, Kayles and Chomp, we didn't need to worry about who is starting, while in that game we need to worry if A starts or B starts and so on. For example, chess is not impartial because white has its own pieces and black has their own pieces. So if white makes a move, white can only move the white pieces, while black can only move the black pieces. So the move sets that are available to both of them are not the same. But in games like Nim and Kayles, there are no pieces of either player. Both the players have to play on the same board and they have the same set of moves. So those are called impartial. And I mean, it's not too surprising that impartial games are very common. The Nim, Kayles, Chomp, all are examples of impartial games. And certainly a lot of games that we will develop are impartial as well. And so, well, okay, one more thing. So, to a Nim position with Nim value n, I'll call, let me write down for its Nim, for its star n. Let me call its value star n instead of just n. And that is for a reason, because when we define addition later on, this doesn't behave like integers, because whatever we define addition to be, this won't be star n plus n, but it will be instead be this. And this will make more sense in the next talk if you come. And so, well, yeah, for now, all that matters is star n is the value to a Nim position, a single to a position with Nim value n. And the Sprague-Grundy Theorem says that this is an informal version, because for whatever we have done today, we have not even defined what a game is, strictly speaking, which we will do in the next thing. And this might seem a little surprising because, well, I'm giving a talk on this thing. I've spoken for 1 hour at this point, and I've not even defined what the main object is. And that is because I think it's very important to work with some combinatorial games directly like this, and then with this, all of this is develop certain motivation, develop certain intuition, and only then it will make sense to define what a game is, because the definition is not the easiest. But it's still, yeah. So we'll see it in the next talk. So let P be a position in an impartial game. we have a position in an impartial game, and the value assigned to that is just star n for some n. And you might think, okay, well, what is stopping me from assigning, well, literally, okay, if you give me a partial game, I'll just say, okay, well, I'll call this position star this, I'll call this position star this, and then this theorem is somewhat trivial. And the point is, I've not said this more precisely, but the assignment of values is not ad hoc. It's not something that I pick this game, I do this for all these positions here. Pick this game, I do that for all the positions here. And instead, define a universal recursive scheme to assign values to any game all at once. And under that universal natural scheme, turns out that the values that I need to assign to positions in impartial games are equal to values that I need to assign to nimpartials. And this is very surprising because all it is really saying is that in this large class of impartial games, including games like Kayles and Chomp, all I need to worry about, if I need to see how they add, how they compare, all I need to do is to look at how star n's compare and how they add. And that is enough to study all impartial games. Well, realistically what happens is, finding this n is a difficult task. So that's what makes still studying impartial games harder. But in theory, well, okay, we are saying that, okay, we are done with studying all impartial games because we know what is going on. So, yeah, and so for the next talk, what we'll do is formally define what a game is, formally write down what this Sprague-Grundy theorem means, and then also prove it. And yeah, so this is it for today's talk. Thank you for attending. Are there any questions?
So we thank the speaker once again.